continuous. I drew it as a loop, but it could be laid out flat where the two ends talk to each other. Each cell has two states. It's either on, like my red one, or it's off, like the blue ones. That's it. They have two states. Every cell listens to three neighbors. It listens to itself, the neighbor on the right, the neighbor on the left. Okay? So that's 8 possible states for any cell. It could be on and it's in some combination of its two neighbors. I'll show you in a minute. And then you apply some iterative rule, and you update all cells simultaneously based on the state of its neighbors, okay? And you just keep doing that, and you get some pretty amazing behavior out of these. Very simple systems. So here's actually, this is Stephen Wolfram's book, A New Kind of Science, which I've glanced through, I haven't read. If anyone's ever seen it, it's like this thick, and it's all about elementary cellular automata. So if you really want to be bored, I think you can do that. So the 8 states are listed there on the left, okay? So I highlighted in the red the cell of interest. But ultimately in this system, every cell is of interest, right? Every cell has a state and has two neighbors. I just picked a random cell. That cell and its two neighbors can exist in 8 different states, and those are the 8 possible configurations, all right? What we want for this system is a rule so that given any one of those 8 states, we can update every cell in the system simultaneously, okay? And so you can imagine a lot of rules. This could be a rule. No matter what the state is, you turn the cell of interest off. That could be a rule. It's pretty boring, but no matter what the initial configuration is, the first step, the whole system will shut off. It's pretty boring. Turns out the notation for that is shown on the right. It's 0, 0, 0 for each of the states. It's rule 0. That's what it's called. But there are a lot of other rules. This here happens to be rule 110. And so the way this works is if any particular cell is in this state here, then it shuts off. If any particular cell is in this state, it stays on, etc. for the 8 states. All cells get updated simultaneously, okay? It's what makes what behavior these rules produce that's what's interesting. It's not the rules themselves. It turns out for an elementary cellular automaton with each cell responding to its two neighbors and itself with 2 states and 2 possible outcomes, there's 256 possible rules, okay? And Wolfram, I decided, is a genius. Apparently he is, but he did this in binary. So all of this is binary. So this number up here for, I guess I shouldn't point, this number right here in binary is 110. So you can figure all of these out very simply. And the rules go from 0, which that really is rule 0, to rule 255. And you can just figure them out if you know binary, which I'd forgotten and I had to relearn because I don't remember my binary. But you guys probably know binary. So it's very simple to do all this. You just have to start thinking in binary again. So what do these rules do? Well, what you do is you look at them with what's called a space-time diagram. And this is an example. Space is along top. This is just each cell is lined up in space, and I show it flat instead of looped around on itself. So in reality, the 2 ends talk to each other, right? This end talks to this end, so that everyone has 3 neighbors. Every point in time is arbitrary in this system. You could set time to be whatever. Every point in time, every agent or every cell updates itself based on whichever rule you've chosen to use. And they all do it simultaneously. And you draw the next line. So in this case, this is the next line if you are applying rule 110 to this initial state. The initial configuration could be whatever you want. This happens to be some initial configuration. And then you iterate this time, and keep going, okay? This is an example of rule 110 over 2,400 time steps with, I think, 800 cells across. The first thing you'll notice, I think, is that it's not just random. It's not just random noise. There's some really remarkable patterns in here that repeat over and over and over and over again. And it turns out Wolfram's proved that this rule, as well as a couple others, are actually universal computers. So if you've learned about Turing machines, I think you do in some class, it's basically a universal Turing machine. It can compute anything. And so it's a pretty amazing rule. But what I want to point out is the rule is very dependent on the neighbors. So this is with each cell talking to its immediate next door neighbors. What if I changed it and said, don't listen to your immediate next door neighbors, listen to the neighbors right next to them? What would happen? Would something different happen? And in fact, it does. It has very different patterns come out of this. And what does this mean? Well, in the brain, when we want to model the brain, we know that each cell or node in the brain has different connections. It's not just listening to its immediate next door neighbors. Those neighbors are all different. And so just by changing the neighborhood, you can change the output of the system pretty dramatically. And so while this pattern looks somewhat similar, it's not the same. As you can see, these stripes going across here continue throughout this system, but they end in this system. And this line right here never shows up in this system. And so it's just by definition of neighbors. So what does this have to do with the brain? Well, Karen has taken these ideas and produced a agent-based brain model. We divide the brain into nodes. We perform a network analysis, like I talked about, correlate with the cross-correlation. We generate positive and negative connections in the network, okay? And those are positively correlated, negatively correlated. And then we simply define our network. And this is an example of a network she built. It's not in any space, but each node represents one of the 90 brain regions, okay? The blue lines are positive connections. The orange lines are negative. And then in this case, some nodes are turned off, some nodes are turned on, okay? Well, what we can do is treat this as an elementary cellular automaton. We have two states. Each brain region is either on or off. We can set it up where there's three neighbors. No matter how many connections a cell has or a region has, we can set it up as three neighbors. Itself, is itself on or off? Then we look at the sum of its positive neighbors, what percentage of them are on, and the sum of the negative connected neighbors, what percentage of them are on. And then we can apply Wolfram's rules. And I think I have an example, if I remember. Yeah. So I picked one node here. It's an arbitrary node, node 83. And I'm showing here all of its neighbors and their states and their connection types, okay? So now, first we can look at all the positive connections. These are the 6 positive connections. It turns out that half of them are on, right? So in this particular cell, 50% of its positive neighbors are on. Has 4 negative neighbors, turns out 75% of them are on, okay? So for this cell, this one node in the network, we have 4 different possible states. We know it's off, right? And then we can set a threshold. We can say, okay, let me say positive off at 60%, negative off at 90%. And then positive off at, or positive cutoff at 60%, there's only 50% on, so it doesn't reach that cutoff, so you put a 0. Negative cutoff 90%, there's only 75% on, so it doesn't reach that cutoff, so you say it's off. So you put 0, 0, 0. And you can get 1, 0, 0, 0, 0, 1, or 1, 0, 1. Does that make sense? Yes. Okay. So we can now take the entire brain and model it with this system. And so now is when I'm going to show Karen's NetLogo brain demo, which is really cool. Everyone in my lab makes fun of me because I sit around and watch this thing. All right. Load the network. Oh, Pete told me, this is awesome. Pete told me one day, before he was giving a talk recently, I don't know if any of you went, Karen was there, I know Kwawi was there, he said, one thing I learned, when you do a demo, the only thing you preface it with is, watch this. Because if it crashes, it crashes. Who cares? You don't tell them it's going to do amazing things. You just say, watch this, because this crashed.